So we have talked about what intermolecular forces are and how they work, and now we're going to see some of the effects that they have. So the properties arising from intermolecular forces include surface tension, viscosity, and capillary action. In case you're wondering, what is this? This is a picture of a paperclip floating on water. You can also get a needle to float on water. It has to be really clean water. But that's due to surface tension. Okay, so what is surface tension? The tendency of liquids to minimize their surface area. It's defined as the energy needed to increase the surface area by a particular amount. We don't need to worry about that. Here we have an illustration or a picture of a trout fly that a fisherman might use floating on the water. Just like the paperclip, this trout fly is more dense than water. It should sink, right? But it doesn't. Have you ever seen those little water skater bugs? They're skating around on top of the water, and you're like, how does that work? It's not like they have big paddle feet or something, but they're just skating around on top of the water. It's surface tension. Let's see how that works. So the surface molecules, this is a two-dimensional look at water. The surface molecules are going to interact with fewer neighbors. Here, this is interacting with 4 neighbors. This one's interacting with 6 neighbors. So there's fewer interactions than interior molecules. For water, that most important interaction would be the hydrogen bonding, right? So they're all attracted to each other. This one has less attraction. Well, because it is attracted to fewer things, it has a higher potential energy. So in order for us to increase the surface area, we have to make more of the molecules high potential energy by having fewer neighbors. And nothing works that way. Balls never roll up the hill, right? They just don't, because that's increasing your potential energy. Things always go towards lower potential energy. Does that make any sense? So the surface tension depends on the strength of those intermolecular forces, right? So if the intermolecular forces are weak, then the surface tension will be less. If the forces are strong, the surface tension will be greater. And surface tension is why water will tend to form a perfect sphere, because a sphere is the shape in which the amount of surface area to volume ratio is the smallest. So this is that same space station guy that we saw the video. Big drop of water just floating in the air. We don't see drops of water that are perfectly spherical when we're looking at them dripping out of our burettes or something, because gravity's pulling on them. But they're trying to be a sphere. And you look at these little droplets on the spider web, and they're making little spheres. They're a little bit distorted. Interesting, have you ever seen one of the old movies where they're using miniatures to do special effects, and there's water involved, like a ship, and there's waves and stuff, and you're like, something's wrong. You can tell, because there's no way to make the water droplets correspondingly smaller, because water droplets are just going to be the size they're going to be. So that's one of the things that makes it always look weird. Another property is viscosity, which is the resistance of a liquid to flow. And again, that can be quantified as well. So in order for a liquid to flow, the particles have to slide past each other. Well, the stickier they are, the more attracted to each other they are, the harder it is for them to slide, right? So I think we all realize that honey, it pours much more slowly than water does, right? You're like, come on, honey, come out of the bottle, right? And it's just like slowly moving. Water doesn't do that. Water just moves right away. Water is less viscous than honey because the honey molecules, the things in the honey, are very much attracted to each other. So if we have strong intermolecular forces, we have greater viscosity. The shape of the molecule will also have an effect on that because the long spaghetti-like molecules can get tangled around each other. And so this is showing us the increase in viscosity as the molar mass increases, as these chains of carbons get longer. Viscosity depends on temperature because at higher temperature, the particles have more kinetic energy, and so they're more able to slide around because they need that extra kinetic energy to break those bonds. So if you take honey and you heat it up, it gets runny, and then you have runny honey. If you take your pancake syrup and store it in the refrigerator, like my mother-in-law stores everything in the refrigerator, you get it out and it pours really, really thick. But if you heat it up, it becomes very, very thin, right? Watery, less viscous. So this is a little table just showing us the viscosity of water at several temperatures. And we see that as you increase the temperature, the viscosity goes down. That's not something we notice because that change is just not that big. An important application of viscosity is motor oil. And when I was a kid and watched TV, there were all these commercials for motor oils, and they always talked about viscosity breakdown. Like it was this thing that everybody's seriously concerned about. We got to worry about viscosity breakdown. So every time I talk about viscosity, I'm like, I hear that voice in my head. It was very successful marketing, except that I don't remember which oil brand they were advertising. Anyway, so regular motor oil, non-synthetic, I'm not going to say it's organic or natural because it isn't really, but just like regular oil, as you heat it up, it becomes less viscous. So your car engine gets hot as it's running, right? And if the oil gets less viscous and it gets too thin, it'll just run off the parts that it's supposed to lubricate. So that's why there are different weights of motor oil, because different seasons, different climates, the engine is going to be in a different temperature range. You also don't want it to be too viscous when the engine is cold. So like, in Minnesota, when it's 40 degrees below zero, your oil, if you don't have the right kind of oil, could be so thick that it's acting more like glue than a lubricant, right? So you have to adjust it. Modern synthetic motor oils are so cool. So they have polymers in them. At low temperatures, those polymers coil up. Well, we saw how the spherical particles, the intermolecular forces attracting them are weaker because there's less surface area. Two spheres just can touch at one point. And then at higher temperatures, they unwind and they become more like, cooked spaghetti. So then they have more attraction, higher intermolecular forces, and so that counteracts the viscosity change due to temperature. And so you can have a motor oil that's going to have a more or less consistent viscosity at a variety of temperatures. It's pretty cool. Any questions? By the way, STP, also a brand of motor oil, besides being standard temperature and pressure. Capillary action. So this is a person having a blood sample taken, a little prick, and the blood starts to well up, and you touch a tube to it, and the blood runs up the tube. It looks like magic. This isn't a pipette where somebody's got a little pump here or something and pulling it up. It just goes up there by itself. That's called capillary action. The ability of a liquid to flow against gravity up a narrow tube. How far up it goes will depend on the diameter of the tube. Here, this one has a very, very tiny diameter, and so the liquid went all the way up there. This liquid is red, but it isn't blood, just in case you don't like blood. that is blood. Wider tube, it doesn't go up as far. So what's going on here? There are two forces. There are cohesive forces, the attraction of the molecules to other molecules in the liquid, that cohesion, sticking together, right? And then there are adhesive forces, the attraction between the liquid and the surface of the tube. So what happens here is the molecules that are close to the tube, the glass, are attracted to it. And they kind of climb up a little bit because they're attracted. And then the cohesive forces mean that they're going to drag their friends up with them. So if you have strong cohesive forces and weak adhesive forces, you won't go up the tube as far. Another thing that capillary action does is create the meniscus. So here we have a test tube with water and a test tube with liquid mercury. It's so pretty and so fun to play with, and unfortunately it's toxic. All the fun stuff. It kind of looks like there's like a contact lens or something there, right? We've seen this. We've talked about measuring the bottom of the meniscus, right? Well, why does the water curve up like that? Capillary action. So the water is attracted to the glass, and so it kind of creeps up at the edge where it's next to the glass. But this tube is not very narrow. It's really large, and so it can only go up a little bit. There's so much interior stuff here that there's no way that adhesive forces can pull everybody up. So it only pulls up the very edge. So in water in a glass tube, the adhesive forces are a little bit stronger than the cohesive forces. This is liquid mercury. And if we look at the surface, the curve is upside down because mercury is not attracted to the glass. So the adhesive forces for the glass are lower than the cohesive forces. The cohesive forces are more important, and so this is trying to minimize its surface area. It's trying to get into a sphere, is what it's trying to do. Any questions?